Hello, my name is Brian Benaj. I'm a second-year aerospace engineering major at the Georgia Institute of Technology, and I'm going to be discussing an experiment we performed regarding the combustion dynamics in a Rijke tube. In this experiment, we worked closely with the type of pulse combustor called a Rijke tube. In a pulse combustor, combustion intensity and heat release fluctuate with time, causing the pressure in the combustor to oscillate in time. Named after the Petrus Leonardus Rijke, the Dutch physicist who invented the device in the 19th century, the Rijke tube is a cylindrical tube open at both ends that uses heat to sustain a sound. The sustained sound is caused by the oscillating pressure in the Rijke tube. On the right, a simple diagram of a Rijke tube can be seen. This type of combustor is advantageous because the combustion intensity is increased because of better mixing between fuel and air, and because it is able to keep heat that would otherwise be lost in the exhaust of a steady combustor. Because of its interesting and advantageous properties, we performed this experiment to gain a better understanding of what happens inside a Rijke tube, as well as how and why this happens. On the left is a diagram of a Rijke tube showing the burner located approximately 1/4 of the way up on the tube, as well as 3 piezoelectric transducers located at different positions along the length of the tube to record the acoustic pressure fluctuations throughout the tests at these different locations in the tube. The transducers are attached to points along the side of the Rijke tube via long, thin tubes that help protect the transducers from the heat in the Rijke tube. On the right is a more detailed schematic of how the devices are connected to the Rijke tube and the electronic equipment that will record the data. The photomultiplier is visible on the left of the Rijke tube. It is positioned before an interface filter that allows light only of our desired wavelength band of around 305 to 315 nanometers, which is the range in which hydroxide chemiluminescence occurs. We conducted the experiment by recording data from all 3 pressure sensors, the photomultiplier, at different heights along the Rijke tube, as well as the flow rate using a rotometer. We recorded data with the burner at different positions along the tube, raising and lowering it with the scissor jack. We first took data at the initial 0-inch position with the valve closed, then again with the valve opened. We then recorded data at the 2-inch station with the valve closed, and finally at the position where pulsation ceased, which in our case was at 6.15 inches. On the left, here the Rijke tube can be seen and heard in action. Notice the continuous humming sound that I mentioned earlier. Just as stated in the lab manual, when heat is added in phase with the pressure oscillations in the tube resonates. On the right is a photo of the flame in the Rijke tube with the valve open. This flame is much taller since there are no pressure waves bouncing down, keeping the flame relatively short. Because of this, the continuous sound also ceased during that test. Since the pressure data was recorded by the piezoelectric transducers in millivolts, I had to convert the data to decibels using the formula on the left, where the PRMS threshold is the threshold for human hearing, which is 2.9 times 10 to the negative 9 pounds per square inch. The converted values can be seen in the table on the top right, where PU is the upper pressure sensor, PM is the middle pressure sensor, and PL is the lower pressure sensor. After this, I used the length of the Rijke tube that we measured in the experiment of 70.5 inches, or 5.875 feet, to estimate its resonance frequency using the formulas for speed of sound and frequency given in the lab manual and shown here. To the right of the equations is the worked out solution for the resonance frequency estimate. Lastly, at the bottom you can see I converted the reading from the rotometer from millimeters to standard cubic centimeters per minute using the table in the lab manual. I then calculated the relative phase angles of the pressure and radiation signals by calculating the difference between each signal and the middle pressure sensor. PMT here represents the photomultiplier. The relative phase angles can be seen in the table to the top right. The tables on the bottom left show frequencies and amplitudes in decibels for the 3 pressure signals and the frequency and RMS of the PMT signal at the 4 conditions tested in the experiment. The frequency decreases as the burner is moved upwards, as well as when the valve is open. This makes sense, since the sound diminishes or ceases at these conditions, the frequency should also decrease. The amplitude of the pressure decreases at higher pressure sensors, except for at the position of 6.15 inches, where it increases because the burner becomes closer to the higher pressure sensor. The long-term behavior of the pressure data throughout each of the tests was very fluid since the piezoelectric transducers can record pressure changes very quickly. The oscillations in pressure were recorded and visible in the data. As the lab manual stated, if heat is added in phase with pressure oscillations, the Rijke tube did in fact resonate. We also saw that moving the burner up along the tube decreased and eventually ceased the sound, just as opening the valve also did. Most importantly, we gained hands-on experience observing and recording the functionality of this interesting pulse conductor. Thank you for watching, and if you have any questions, you can direct them to my email shown here on the screen.